Alright, so whatever this turns out to be, 12 pi. And I changed the limits of integrals. This is like all things we've been practicing kind of problem. So then this is so I think you get something kind of like gross in the end, right?
Get 12 pi times 4 over 5 minus 16 over 3 plus 4.
Let's see, I messed up yet. So that's 12 pi times. Oh boy. So what is all that crap?
It's like 4.
5.
Oh, yeah. Sorry, height.
You chose this right?
Yes. No,
Like 48.
you're missing a 4.
Wait. No, I'm not. Or am I? Where's the minus?
You forgot to add 4. Or add 48 pi.
Did you get 16 pi times 5 minus 1?
Wait, I got. Oh, I guess what I did is just like the same thing.
Wait, did you get what I just said now? 16 pi times root 5 minus 1?
Yes.
Like, yes, actually? I think that's right. I can like look up that. Someone back me up. Who's like fast and like doesn't make mistakes.
4 thirds root minus 16 plus 4, 12, yeah, that's right.
Pretty sure that's right.
It is.
Good, get your senses right. Alright, so good. That was like very slow. But whatever. I don't know, I had an answer somewhere, but I think it's right. Alright, forget what I get, you just copy what I do. A little bit of both.
That was pretty good.
Alright, good. We got 6 minutes. Let's do something else. There's a couple more homework problems due today. Let's do like 2 of them or something. Sound good?
121.
121. Excellent suggestion. They're kind of like very similar to each other, these 2 problems. You get, yeah, 107 and what? Sorry. Wait, Hannah, you thought which one was the harder one? You thought?
Oh, I would like going over a 121, please.
Yes.
If possible.
Okay, yeah, I agree. Okay, so I can do 117. Let's go.
Could you also do 121?
Okay, sure. I can do anything. 117 is the integral from 0 to 7 of x times the cube root x plus 1 dx. Okay, and then someone make sure the camera's like on screen and stuff. 121 is the integral from pi over 2 to 2 pi over 3 of secant squared x over 2 dx. All right, in both of these, we have some work to do. Let's go. First of all, what is the relevant substitution here that will make everything wonderful?
U equals x plus 1.
Yeah, like u equals x plus 1. Some experience is required to see that that's like a really good idea, but it just like is a good idea. If you let u be x plus 1, good. Then x is just like u minus 1, and du is just dx. So I can transform this problem into, well, x becomes now u minus 1, and cube root x plus 1 becomes cube root u du.
Wait, it's a cube root?
It is.
Wait, so it's not x cubed times square root of x plus 1?
Nope.
Oh, I did the wrong bubble.
Good. And then here we put in u of 0, and here we put in u of 7, changing the roots as we go. Now, you might think, wait, we haven't really made any progress, because we had a problem, which was like linear times the cube root of linear. Technically not talking. And now we still have a problem, which is linear times the cube root of linear. So like, I haven't fundamentally changed the problem in any kind of deep way, but I have turned it into something which is now very, very doable. Because now I can just multiply cube root u through and then do it in like pieces, yeah? So what is u of 0? U of 0 is 1, and what is u of 7? It's 8. So I've changed the limits from 1 to 8, and now this becomes u to the 4/3 minus u to the 1/3. And when you write it like that, this is now a relatively straightforward integration problem, yeah? You just have to be able to anti-differentiate this, and we all know how. Upper power gives you 7/3, and so this is like 3/7 u to the 7/3 minus 4/3 u to the 4/3.
3/4.
3/4. What happened? That should be 3/4. Woo! And then I evaluated at 8 and 1. And I guess these like work out nicely, right? Because what I end up with is like 3/7 times 2 to the 7th. So that's 128 minus 1 minus 3/4 times 16 minus 1. Does everyone see what I did there? That was like relatively sophisticated-ish, what I just did. To get from here to the final step, it was just like more convenient because fractions are annoying to do like this one at 8 minus this one at 1 minus 3/4 times this one at 8 minus this one at 1. If you do it a different way, it's all the same. You just have to keep track of your parentheses and negatives and stuff. Who is good? Say good.
Now that you know what the problem is.
Okay, so good. Patrick is very upset about something that's his own fault. Good. The worst, that's what usually when people are really mad, it's because they're mad at themselves. Whoa. Wisdom from an adult. Good. How do we do this next problem? Well, I'm going to let u be x over 2 because that seems like a good idea, and therefore du dx is like 1/2. So I shall, can I get a purple or blue marker? Throw. Woo! Oh.
That was almost.
So I need a 1/2 in here, so I'll stick it in and I'll undo the damage with a 2. Well, therefore this problem becomes 2, and I'm very careful to change my limits right now, so that's u of pi over 2, and that's u of 2 pi over 3, and here I just get secant squared u du. And so this problem becomes 2 times, well this problem is just halving, so this is just like pi over 4 to pi over 3 of secant squared u du. So all I did was just do a little small variable substitution, u equals x over 2. And now the problem is basically done, because what does the antiderivative of secant squared? 10. And so this whole thing becomes 2 tan u evaluated at pi over 3 and pi over 4. Is everyone feeling good about this substitution thing? It's really nice if you do it the good way, because then you have like hard integral, and then you have like simple integral, and then you just do it. Right, so whatever this turns out to be, this is 2 times root 3 minus 1. Done. Woo! All right, goodbye people watching at home. Math.